Y to delta or delta to Y transformation. And we're also going to talk about pi to t, and sometimes this is called star delta transform. All right, all those mean the same thing. First, let's talk about what they are. Wye-Delta is probably the most common term used to describe these types of resistor networks. So let's say that we have terminals, three terminals, terminal A, terminal B, and terminal C that are connected up with resistors this way. So we have terminals A, B's, and C's. You can imagine that there are wires coming off of there if you want to. But these resistors are named, and the order in which they're named is important here. This is terminal A, what we're calling terminal A, then this will be resistor A across the triangle from terminal A. And then resistor B will be this one over here, and resistor C will be this one over here. So if you've got terminals A, B, and C labeled like this, then resistor A, B, and C are going to be labeled like that. Okay, that is a delta. That's a triangle. This can also be redrawn like this. There. This on the right-hand side is the same as this on the left-hand side. If this is terminal A, and this is terminal B, and then down here all of that node is terminal C, then the resistor across is terminal C, the resistor across is R sub B, and the resistor across from the A node is R sub A. So this, if you look at it, looks kind of like a pi. So that's where the name pi comes from. So a delta and a pi are really kind of the same thing. Also, let's talk about what the Y is. A Y can look like this. It's really kind of obvious why it's called this. These terminals are named the same. So there's terminal A, terminal B, terminal C. But the resistors are different, okay? We have a different assembly of resistors here than we do for this up here. So let's call this resistor 1. That's by the first letter of the alphabet. R1 goes with A. R2 then goes with B. And R3 then goes with C. Then once again, if you label your terminals A, B, and C like this, then R1, 2, and 3 must be in this order with this configuration. Now that's a Y, and obviously that's a Y. Some people think of that as a star as well, I guess, so that could be considered that. Also, if you rearrange the resistors, you can redraw it this way, where now this is terminal A, terminal B, terminal C, R1, R2, R3, like that. So you can see all I've done is take the upper portion of the Y and spread it out so that it looks like this. And that's a T now. So you can see that a Y and a T are really the same thing, and a delta and a pi are really the same thing. Now, in fact, any three resistors that are connected to a single node could be considered a Y or a T. For example, this one right here. There, same thing. This could be terminal, let's say that's terminal A, terminal B, terminal C. This would be R1, R2, R3. So there, once again, because they're all connected to a single node, the way they would be here or here, all three of those there are essentially the same. You saw that that's like 1/2 of a Wheatstone bridge. That's what they're called, Y-delta, pi t, star delta. What's not so obvious, though, from this is that the delta can be transformed into one of these. Okay, the delta pi up here can be transformed into a YT down here. All right. Now, that's not obvious. But if you'll think about this, let's say that we just concentrate on these two over here. These two can be transformed. If I put my digital multimeter here, one probe here and the other probe there, then I'm going to read some resistance value depending upon what R, A, B, and C are. If I put the probe here and here, in order for these two to be equivalent, I have to get exactly the same resistance value. And the same as if I went from A to C. I would have to get the same resistance, and B to C. In other words, all of those terminals would have to read exactly the same, and if that's the case, then this circuit is equivalent to this circuit. That means if I redraw, let's redraw this circuit right here and just concentrate on what's happening between terminals A and B. I'm going to redraw it. So you can see what I've done here. I've taken this and I've redrawn it. Terminal C is not important because we're only interested in what's happening between terminals A and B, but terminal C would be right here and it would come off right down here. And then you can see that across from terminal C is R sub C, across from terminal A is R sub A, across from terminal B is R sub B. So this is equivalent to that, just redrawing it a little differently. Okay, well, that is the delta redrawn. And if I'm interested in what's happening between terminals A and B, then that has to be the same as this. And now what I've done is I have taken this circuit and redrawn it this way because I'm only interested in what's happening between terminals A and B. I didn't redraw C, but if I did, it would just be a resistor dangling down here. It's not connected to anything. I'm only interested in what's happening between A and B. So the third resistor here plays no role in that. Now, ultimately what I want is, like I said, take a digital multimeter, put it across here, measure the resistance, put it across here, measure the resistance, and those have to be equal to each other in order for these two circuits to be equivalent. Well, let's write down the resistance between A and B. Well, up here, the resistance between A and B, you look at it, you can see that we've got these two elements down here that are in series with each other. So the equivalent of those two is just going to be the sum. But then that combination right there is in parallel with this. So I could write that as product over sum of all of this together. So this is going to be R sub A plus R sub B, that's the series portion, multiplied by R sub C over the sum R sub A plus R sub B plus R sub C. So this is nothing but product over sum for this parallel system here, but A and B have already been combined here. Okay. Now that's RAB for this circuit. Let's do RAB for this circuit over here. Well, that's easy. That's just R1 plus R2. Now, if these two things are equal, then it must be the case that RA plus RB times R sub C, that's a B, divided by RA plus RB plus RC must equal R1 plus R2. That must be the case. Okay, now we did that just for terminals A and B. But in order for the entire circuit to be equivalent to this entire circuit down here, then it must be the case across all the terminals. So the resistance from BC up here, if we were to redraw this with terminal C down here, well, the resistance is going to be, and over here, if we were to do the same sort of thing with another resistor, terminal C, and this is going to be resistor 3 there, then R between B and C is just going to be R2 plus R3. So those two things must be equal then as well. And if we were to do it for R between A and C, that's going to be, let's see, RA plus RC times RB over RA plus RB plus RC. And over here, the resistance between A and C is R1 plus R3. And again, those must be equal. So this is equal because of RAB. this portion here is equal to this portion here, because RBC must be the same, and this portion here is equal to this portion over here. Why? Because the RACs must be the same. These are my three equations that are going to allow us to transform from one of these into the other. And then the terminal behavior, terminal-wise, these will be equivalent circuits. So how do you do that? Well, there's some math involved. We're going to skip a lot of steps here, and I'm going to jump to the final solution. You can transform from the ABC side to the 1, 2, 3 side, or you can go from the 1, 2, 3 side to the ABC side. So let's say that R sub A, R sub B, and R sub C are known values. Their values are known, and we want to transform to the Y network. So this would be part of the delta. We're transforming to a Y then. So R1 is there. You can solve for R1 out of those three equations. And when you do that, you get this. RB, RC over RA plus RB plus RC. So if you solve for R1 out of those three sets of equations, you get this. If you solve for R2, you get this. And if you solve for R3, you get... So if R, A, B, and C are known values and you want to transform from a delta into a Y, then you would use these equations here. Okay, these are your transformation equations. Now, there are some patterns here. I think you can obviously see that R, A, B, C, the sum of those appears on the bottom of these fractions every time. So that part should be pretty straightforward. That's just the sum of A, B, and C. However, the top, you've got BC up here, you've got AC here, you've got a B here. So what's the pattern there? Well, once again, if you think of 1 as belonging to the A, you know, A is the first letter of the alphabet. Well, R sub A is the thing that's left out here. So you write the product of B and C up here. And down here, the second letter of the alphabet is B. B is the thing that's left out, so there's no R sub B on top. C is the third letter of the alphabet, and R sub C is missing from the product at the top. That's just a pattern. If you can spot that pattern, then you may be able to write these down and then use them for transformations. Now, if you went the other direction, for the other direction, R1, R2, and R3, those would be known. And in that case, you end up with equations for R sub A, R sub B, and R sub C. And here's what they look like. There are your transformation equations when you want to go back the other direction. And once again, there is a pattern here. Remember A, first letter of the alphabet? Well, there's R1 on the bottom of the fraction. B, second letter, R2. C, third letter, R3. The tops are the same for all of these, and that's just every permutation. So every combination of the three resistors, 1, 2, 2, 3, 1, 3. And they're multiplied together and then summed up. So if you look for those patterns here, you may be able to distinguish between these two, with these two sets of transformation equations. All right, well, now that you've seen Y-delta and delta Y transformations, then let's use them to solve a circuit. Let's say we have a circuit that looks like this. So here we have a 2 amp source and a network of resistors with various values. Now, what I want to find here is the voltage across the source. Now, I is known, but we can't find V unless we're able to do something else in the circuit to determine that. We cannot determine what V is just by inspection here. It's going to be difficult. Now, V is unknown, but it can be found through Ohm's law, V equals IR. As long as we can find an equivalent resistance for all of this stuff over here, we can reduce it down through perhaps series parallel reduction, Wye-Delta transformations, whatever, to find an equivalent resistance, and then we can determine V. I is just going to be 2 amps at that point. So if we can find the equivalent resistance, no problem. But if you look at this, there is nothing here that is in series or parallel. Nothing whatsoever that we can combine using series parallel reduction methods. However, you might notice there is a big T right in the middle of this. So this would be one way to solve this circuit. That could be a terminal, that could be a terminal, that could be a terminal. So there's terminal A, over here's terminal B, here's terminal C, like that. Okay, if this is terminal A, then this is resistor 1, this is resistor 2, and this is resistor 3. So what does that mean? That means for our purposes here, resistor 1 is 20 ohms, resistor 2 is 10 ohms, and resistor 3 is 5 ohms. Now, we could replace this then with a delta. Now let's redraw that and see what it would look like as a delta. There, this is still terminal A, this is still terminal B, and this is still terminal C. But at this stage, this is now R sub C, this one is R sub B, and this one is R sub A. Now we'll have to calculate the values for our A, B, and C, given R1, R2, and R3 here, but we can do that. I'm going to save that, though, for a moment and continue on to see if this actually helped us any. And if you look, you see it has helped us. For example, R sub C and the 28 ohm are now in parallel with each other. Something else over here, the 105 and R sub A are in parallel with each other as well now. So we could combine those. So when we combine those, we're going to have a resistor that is the combined 28 and R sub C. Let's write that this way, 28 parallel R sub C. And then over here is still the 105. I'm sorry, the 105 that's in parallel with R sub A. So it's not 105 alone, it's this combination here. That's this resistor. And then there is still R sub B going across here. So all I've done at this stage, I haven't computed R, A, B, and C yet, but you can see that this is a combination of these two resistors. This is a combination of these two resistors, and I've just redrawn the circuit this way. All right, at this stage, you'll notice that this one is in series with the 28 parallel RC. So I could combine those two together. And when I combine those two together, let's see, what does that look like? So this is still R sub B. This is still the 2 amp source. All I did is kind of move R sub B around, put it in this position. But this one over here is the combination of these two put together. So what is that? That's the 28 parallel R sub C plus the 105 in parallel with R sub A. Okay, at this stage then, we should be able to combine these two together because why? Because those two are in parallel now. So we can go up here and redraw the final circuit with one resistor. And now what is this one? Well, it is R sub B in parallel with the 28 parallel R sub C plus 105 parallel R sub A, parenthesis close. All right, so now if I know what R sub A, R sub B, and R sub C are, well, what can I do? I can combine these. So let's think about that. I need to combine those two right there, these two right here, and then that combination when I sum it together with R sub B. Okay, let's do that. Okay, so I'm going to rewrite R1 is 20 ohms, R2 is 10 ohms, and R3 is 5 ohms. I want to compute R sub A, R sub B, and R sub C. Let's start with R sub A. That's R1, R2 plus R2, R3 plus R1, R3. All that over R1. Okay, so R1 times R2, that's going to be 200. Plus R2 times R3, that's going to be 50. Plus R1 times R3, that's 100. Divided by R1, which is 20. So that's 200, 350 divided by 20. So R sub A is 17.5 ohms. Let's do the same thing for R sub B. Now the top part of the fraction is going to be the same, so it's going to be 350 divided by R2, which is going to be 10. So this is going to be 35 ohms. Then R sub C is going to be 350 divided by 5, so that looks like it's going to be 70. Okay, so we've got our three values for R, A, B, and C. Now we're ready to tackle this right here. We have R sub B, and that's in parallel with the 28 parallel RC plus the 105 in parallel with RA. Well, let's do the 28 parallel RC first. That's going to be product over sum. So it's going to be 28 times 70 over 28 plus 70. And that turns out to be 20 ohms. Now let's do the 105 parallel R sub A. That's going to be 105 times R sub A, which is 17.5. That's 15. Now we need to add these two together to get what's inside the parenthesis here. So that's just going to be 35. So 35 ohms is what's in the parenthesis here. So we have R sub B parallel with 35. So R sub B is 35, and that's in parallel with a 35. Okay, this is going to be interesting. You can easily figure out the answer for this one. It's just going to be half of that. But let's go ahead and show that that's the case. 35 times 35 divided by 35 plus 35. Well, you've got 35 times 35 divided by 2 times 35. You'll notice the 35s cancel, and we just left with half of 35. So that is 17.5 ohms. That is what this combined equivalent resistance will be right here. Now we need to figure out what the voltage is. Voltage is going to be I times R, where I is 2 amps. So V equals IR. It's going to be 2 amps times 17.5 ohms, and 2 times 17.5, 35 volts. Final answer for this question, what is the voltage across the 2 amp source? Answer, 35 volts. We were able to do that using Wye-Delta transformation, whereas we couldn't just use series parallel reduction here because there was nothing that was in series or parallel in order to accomplish that. Okay, so now you've seen another trick for simplifying circuits so that you can solve them more easily. And that's the end of Wye-Delta.